Okay, let's look at some example of operational amplifier circuit. Example. So let's have the simple. So this is the one we have in the first up-end filter lab. So I want to know what's the relationship between the output voltage and the input voltage. Okay, so let's do a modeling or analyze this circuit first. So let's mark this point here, E negative, this point E positive. So if I look at this point A or node A, at node 8, so current in equal to current out. So let's define it's I1, I2, and the one go into the terminal, that's IA. So current in I1, current out I2 plus IA. Now what's I1? I1 will be voltage difference across the resistance divided by the resistance. So voltage difference would be VI minus at point A, which is E negative. VI minus E negative divided by resistance R1. How about I2 from point A to V naught? So voltage difference E negative minus, make sure the flow direction, the current direction is from A to this point. So it should be E negative minus, because it's going out, divided by R2 plus IA. So this is typical Kirchhoff current law or node law. Okay, so let's apply the two principles to analyze the circuit. Up-end circuit, like we mentioned earlier, what would that be? First one, let's do the second one. The terminals, the current flow through into the two terminals is 0. So IA from E negative to E positive, this IA should be 0. So let's cross this one out, equal to 0. The other principle, E positive equal to E negative, right here. Okay. But in this particular case, E positive is connected to ground right here. This one is connected to ground right here. So this is 0. In this case, it is 0. Okay. Now, in other words, E negative is also grounded. So this is 0. It's 0. So we simplify this. So we can get 2 VO over VI is minus R2 over R1. Okay, so this is very useful circuit. And okay, what is this circuit for? Okay, somebody might tell me that in the lab we say it's a simple gain, but there's a minus sign here. So yes, it could be a gain and implications. However, you do have a minus sign. So in this situation, most of the application for this is if we set these two are equal, what do we have? DO equal to minus VI, which is total. We have the output will be the minus sign times the input. In other words, this is typical. This circuit is typically used as a inverter. Invert the sign. Invert the sign. Okay. So following the same principle, now if I have a circuit, if this circuit can be analogous to this one, let's say instead of resistance, if I can make it in terms of impedance concept, V out. Impedance concept. Let's try not to be. So this is another news. Impedance concept. So what's the relationship between output voltage and input voltage, VI? And the same approach that we did before, except this time we use impedance concept. So simply we can get exactly the same answer, but it's in Laplace domain. Capital V out, VIS, which is our transfer function, of course, will be minus R2 over R1. So in this case will be minus Z2 over Z1. Z2S over Z1S using impedance concept. Okay, so in other words, as long as if this circuit can resemble to this one, automatically we can get a transfer functions minus Z2 over Z1. Keep it in mind when we use impedance, resistance still in Laplace domain impedance, resistive impedance still R. Capacitance, we call capacitive impedance will be 1 over CS. And what the other one? Inductance. Even though we don't use inductors in the op-amp circuit, but if in general impedance concept, inductive impedance will be L times S. Okay. So let's look at next example. So let's do quick one. What is this one for? And so what is this circuit? Or what's the relation between these two? So again, now we can treat this one as a big impedance Z2. This is impedance Z1. And V, again, Laplace domain. So O in capital variable minus Z2 over Z1. This is Z2, which is capacitive impedance, so should be minus 1 over CS. This resistive impedance will be R, so be minus 1 over RCS. Okay, so what is this circuit for? Okay, if we design the circuit, well, we simply can let RC value equal to 1, which give you the relationship VOS equal to 1 over S times VIS. So Laplace domain, let's do it one more time. SVO minus VIS. Okay, 1S in Laplace domain. In time domain, that's derivative. So this would be S in time, this is Laplace domain. Time domain dV minus VIT. In other words, what's VO? So VO should be so what is this circuit for? Your input and output will be integration of the input signals. So this is what we call as an integrator. Integral or integrator. Okay, and minus sign can be corrected with another Arduino inverter. So you invert the sign, that's fine. Okay, so following the same concept, if we do another one, what is this circuit for? This up-band circuit for? So same things, output in Laplace domain over input should be minus Z2 over Z1. In this case would be R over 1 over CS. Okay, would be flip, should be minus RCS. Again, if you set RC equal to 1, so VOS equal to minus VIS, minus S in the front. Again, 1S right here. In time domain, that's derivative. So time domain VOT will be minus D dt VIT plus time domain. So what is this circuit for? This is differentiator, derivative differentiator. Differentiators. So let's continue another example. Let's see. Out VI. So what would be the relationship between these input output VO V in? again, we can treat this Z2, this is Z1, and now inverting terminal is ground, so it should be analogous to the one we just showed earlier. So VO over VI in the plus domain should be minus Z2 over Z1, so minus Z2 will be two impedance in parallel, so the equivalent one should be product over summations, so should be R2 times 1 over C2S product over R2 plus C2S 1 over C2S product over summations. These are the equivalent one. Two impedances are in parallel, in series, should be adding up together. So R1 plus 1 over C1S. Okay, so if we further simplify, will be minus. So C2, C1, R2, C1S, R1, C1S plus 1, R2, C2S plus 1. Okay, so we get a transfer function, which is output over input. Definition of transfer function, which will be this one. And if you already had up-band lab, filter lab, this is actually the bandpass filters. The purpose of this circuit is for bandpass filter, but we'll talk about that later more when we deal with exactly bandpass filters. Okay. Let's continue with another circuit, which is let's see. Now, if I have 3 input, V1, V2, V3, V out. So what would be the relationship relating output voltage to the 3 input voltage V1, V2, V3? Okay. Well, let's do it step by step. Let's just consider that this point A, okay, E negative, E positive at this voltage, and then we have I1, I2, I3 at this point A, so you have IA and then I4. Okay. One more time. Kirchhoff current law for current in equals to current out. So at node A, I1 plus I2 plus I3 equal to I4 plus IA. Coming in 1, 2, 3, coming out I4 and IA. Okay. So what's I1? I1 will be voltage difference between V1 and point A, which is E negative. voltage difference, so should be V1 minus E negative R1. So same things, R2, V2 minus E negative, 3, V3 minus E negative, R3, equal to I4 from point A, E negative 2 outwards. So point A, E negative to this point, V naught. So E negative minus V naught over R4 plus IA. Now let's apply the principle of the two principles of analyzing op-amp circuits. IA equal to 0, so this one goes away. Another one, E positive is always equal to E negative. And in this case, what's E positive? E positive is here, is grounded, so this is 0. Grounded, E positive. You put it here. So E positive is grounded, so it's 0. Of course, then E negative will be 0. So put this one back here, so this is 0. This is 0. 0. 0. Okay, let's further simplify. We get let's further simplify. We get VO equal to minus R4 over R1 V1 plus R4 over R2 V2 plus R4 over R3 V3. Okay, so what is this circuit for? Well, if you design the circuit, you can set the values. So first one, if you set R1 equal to R2 equal to R3 equal to R4, what do we have? We have V out equal to minus V1 plus V2 plus V3, which is summation I equal to 1 to 3 VI. So what is this circuit for? Well, we can take this minus sign away because we can always use inverter to invert the sign. So this circuit is a summation of 3 voltage 1, 2, 3 V in 3 voltage 1, 2, 3. So this is what we call a summation or summer, or actually the summation side or summation. We can use this circuit to add the signal together. Okay, that's one application. Of course, we have another application. Let's see. What if we make R4 equal to 4, R1 equal to 2, R2 equal to R3. If we put this one here, and again, let's put this number back in, what's VO? VO equal to minus 4V1 plus 2V2 plus V3, right? This might not be clear, that what is this one for, but let's say if the input voltage is always the same, so let's say it's minus, and then put 4 in terms of 2 square plus 2, 1 plus 2, 0 raised to 0 V in or V1. So what is this one for? This is what we call this is for the analog to digital, digital back to analog signals. Okay, DA converter. So in other words, I can generate a circuit with on-off. It's closed, connected, it's 1. Open, it's 0. Okay, so if I have a circuit, let's say it's a so V reference. So if I make 4R, this is R, this is 2R, this is 4R, on off. In other words, I can, through the control, I can make based on this one, on off. I can use this one as a control. VO will be equal to minus so this times this. Okay, so if I have a binary code of 1 0 0 1 0 0, meaning this gate right here is closed, connected. This is open, open. So this one will give me a corresponding negative. This is negative voltage. Okay, so this is binary. In other words, this is digital to analog converter. And we will talk about more. We'll talk about ADDA converter, but this is another application of this op-amp circuit. You can convert the binary numbers back to analog voltage, binary code. Okay, and this is what we call 3-bit. Each one of bugs considered to be 1 bit, so you have 3-bit DA converter. Okay, so this is some basic application of this circuit.